Okay, so in a previous video, we went through for this sort of pulse signal, and we showed how we would calculate the alpha n values, the Fourier series coefficient values that would allow us to sort of synthesize an approximation using the complex form of the Fourier series. Let's say instead that I wanted to be able to express it as a sum of shifted cosines. So that basically has this formula right here. All right. So if that's the case, what I've said previously is I can relate the series to each other. We said there's multiple versions of the Fourier series. I've always said the shifted cosine is the most intuitive for analysis with circuits and systems. Because if I put a cosine waveform as a voltage into a circuit consisting of R's, L's, and C's, what's going to happen is the output voltage or the output current of that circuit is simply going to be shifted and scaled. All right, it's going to be another cosine function that's been shifted in phase and scaled in amplitude. So it's the most intuitive for understanding what's going to happen in a circuit. There's also what we call the complex series, right? They said that's the simplest one for analysis. And then we have the sine-cosine series, which is just kind of annoying. The math is ugly. All right, the math, the calculus is very simple when we have exponential functions. So we like this guy. So in this case, what I'm being asked to do is to go from the complex series to the shifted cosine. And if I had to, I would then go from the shifted cosine to the sine-cosine series. All right, so I showed previously that I could use Euler's identity, all right, to be able to represent the complex series and relate it to the shifted cosine version. All right, so we basically have gone through this formula before. All right, so I'm going to go ahead and try to do that. Again, this just uses Euler's identity. All right, so I need to basically figure out for each of the alpha n, I can relate the magnitude of alpha n to Cn over 2, and I can relate the angle of alpha n to theta. Okay, so let's try to do that. All right, so previously, this was our alpha n right here. Okay, so if that's the case, that is a complex number, right? So I should be able to determine the magnitude of that complex number. Now, the way you get the magnitude of a complex number is you say, well, take the magnitude of the real part squared. So the real of alpha n squared plus whatever the imaginary part of alpha n squared is. Okay? Well, that means I got to convert alpha n into something into rectangular form, and this guy is not in rectangular form. So let's try to do that. All right, I could say alpha n is 1/2 minus e to the negative j n omega naught. Now, how do I get that guy into rectangular form? Well, I get him into rectangular form by remembering Euler's identity, which is e to the j theta is cosine theta plus j sine theta. All right, so that this, if I use that here, alpha n must be 1/2 minus cosine of negative n omega naught, right? So up here, basically it's like theta is equal to minus n. So theta is minus n omega naught, okay? So I say plus j sine minus n omega naught, like that, okay? I keep going. So this is 1/2 minus cosine. So cosine of minus n on cosine of a negative angle is the same as the cosine of the positive angle. So I rewrite that guy like that. The sine of a negative angle is the same as the negative sine of the positive angle. So I write minus j sine n omega naught like that. Okay. That guy simply becomes 1/2 minus cosine n omega naught plus sine n omega naught times j, like that. Okay? So what I see from that, the real part term becomes complicated. It's got two terms in it. The imaginary part term is just that. Okay? So that tells me right there that alpha n, the magnitude of it, is the square root of 1/2 minus cosine n omega naught squared plus sine squared n omega naught, like that. Okay? So I can put all that together, all right? And I said that Cn over 2 equals magnitude of alpha n. So I know that Cn has to be 2 times the magnitude of alpha n. Okay? Now, theta n, we said theta n is equal to the angle of alpha n. So that's the angle of 1/2 minus e to the negative j n omega naught. Okay? So I have the angle of the sum of complex numbers, right? So one complex number is 1/2, the other is minus e to the negative j n omega naught. Well, what's the angle of 1/2? The angle of 1/2 is 0. Okay? Then I'm going to say plus the angle of minus 1 times e to the negative j n omega naught, like that. Okay? I did it that way on purpose. What's the angle of minus 1? Well, the angle of minus 1 is 180 degrees. And the angle of e to the negative j n omega naught is minus n omega naught. Okay, because remember, this guy up here is theta. So our theta is minus n omega naught, like that. Okay, now one important thing to remember is if I have e to the j theta, that theta is in radians by definition. Okay, this guy becomes cosine theta plus j sine theta. The definition always of a trigonometric function is that the argument of that trigonometric function is in radians. So that means that this guy is in radians, this is in degrees. So just to make everything simple, I'm going to say that it's pi minus n omega naught, and all of this is in radians. Okay? All right, so I'm going to make sure that I do this way. All right, so at this point, I'm almost ready to go into MATLAB using this expression, or I guess I should say this expression, Cn equals 2 times alpha n, and this expression for my alpha n, and then also this one here, that theta n equals pi minus n omega naught. All right, so I'm almost ready to go. There's one caveat that I should be careful about, right? What happens at n equal to 0? Okay, what happens at n equal to 0? So let's be careful about that for a second. So let's just go to the alpha n expressions for a second. So the alpha n expression is this integral over a period x of t e to the negative j n omega naught t dt. Okay? If I look at alpha 0, so in other words, I plug in n equal to 0. Well, plugging in n equal to 0 makes this exponential term basically become 1, right? Because I just have e to the 0. So that means that alpha 0 is by definition the area under the curve over a period divided by the period. This is by definition what I call the average, I write that in brackets, of x of t. Right? That's the average value, or sometimes what we call the DC value. Okay? If I look back at the shifted cosine version of the series, right? If I look back at that, I have this C naught over 2 plus this summation of cosines. Well, what's the average value of any cosine function over a period? It's always 0, right? So cosine of omega naught, or 2 omega naught, or 3 omega naught, or 4 omega naught, over one fundamental period, the average of that guy is always 0. You learned that when you first learned sine and cosine. So that means that if I took the average of f of t, so the average value of f of t over any period, it would be C naught over 2. All right? So what that tells me is C naught over 2 is the average value, so that must also be equal to alpha naught. Okay? So what I'm going to do here is remind myself that I have these relationships, but alpha naught, which I calculated, so alpha naught is basically my alpha n. So my alpha n is just 1/2 minus, what is it? Where's the actual, okay, here it is here. 1/2 minus e to the negative j n omega naught. So e to the negative 0. So 1/2 minus 1 equal to minus 1/2. That is equal to C naught over 2. Okay? So what I'm just going to do is C naught over 2 is equal to alpha naught. That's the average value. I'm just going to add that in. So in my code, I'm going to basically have code for n equal to 0 and code for n not equal to 0. Now if I just Google how do I write not equal in MATLAB, I put tilde equal like that. All right, so let's put this over here. All right, and let's go through and look at the code that we wrote. So down here, I did my code. So I created a new vector, x2. And I'm going to do this for 400 harmonics. Okay. In this case, my loop goes from 0 to 400. Right? I don't need to include the negatives now because I have a cosine function. If I complex exponentials, it takes a complex exponential, the positive frequency and the negative frequency together to create the full harmonic. Right? I don't have to do that if it's a cosine. Okay, so I start at 0, right? And that's clear in the formula, right? So there's the formula there. You see I go from n equal 1 to infinity. So again, I'm approximating, so I'm going from n equal to 1 to something different, to n equal 1 to 400, right? Because I'm approximating the function. All right, so you look at what I did. So here's our alpha n, and I said Cn equals 2 times that. So that's what I have as the first line in the for loop. And then I compute my theta value, which is pi minus n omega naught. That's what I have here. Okay. And then I have my if statement. So I say if n is not equal to 0, I have x2 is equal to whatever the old x2 is, plus c times cosine n omega naught t plus whatever theta is. Okay? Now, if n is equal to 0, what I do is I add the average value of the waveform, which is minus 1/2. Okay? So what we said up above here is, remember, alpha of 0 is always the average value of the waveform. And the average value of the waveform is C naught over 2 in this form. I don't really care. I could determine C naught and then divide it by 2. All right. But I'm just careful because I'm going to add in the just whatever the average value is that I've already determined, which is minus 1/2. Now I'm careful to do this one differently because if you look at the way that I derived the formula for relating alpha n and Cn, it assumed that I had basically a cosine. At n equal to 0, I don't really have a cosine, right? So I'm just treating that one special, right? And just making sure that I understand what it means to be the DC value, all right, which is the average of the waveform. All right, so let's evaluate all of this. Okay, now I can see that the red and the blue basically sit on top of each other, okay, which is exactly what I would have expected to have happen because the two forms of the series are equivalent. If I wanted to, I can now use my Cn and theta n values to also go through and do the shifted, the sine and cosine version of the series. Okay, that's not too hard to do, right? Basically, all I would have to do is calculate for myself an an and a bn, and an values are simply derived from Cn cosine theta n, and bn is minus Cn sine theta n. All right, and it wouldn't be hard for me to do that at all. If I wanted to try to do that real quick, I could. All right. So one thing I could do for myself is I would just go through and let's say I did this. I'll create a vector x3. I'll do it for 400 harmonics again. And let's say I just keep the same exact expression that I had before for C and theta, but I just say let's let A be equal to C times cosine theta. I'll let B equal to C times sine theta. Of course, there's a minus sign in that one. And I'll do the same thing. So if n is not equal to 0, x3 equals x3 plus a times cosine n times omega naught t plus b times sine n times omega naught times t, like that. And then when n equals 0, I'm just going to add in the average. Okay? And let's put t and x3 in that graph. All right, so let's run that. Now I have three things sitting on top of each other. So the yellow just appeared on top of the red. Right, so I can see easily how to get in between the different forms of the Fourier series. And like I was saying, it was a pretty trivial jump to go from shifted cosines to sine cosine. The work was really in getting between the complex version of the series and the shifted cosine series. All right, I think it's just simplest to remember those relationships. Remember how I can go from sine cosine to shifted cosine to complex, or from complex to shifted cosine to sine cosine. Simplest way to do it.